So here we have this analysis, again this observation. All stable matter in the universe appear to be composed of constituent fermions. Again, this can be a bunch of quarks. It can also be leptons. And they attract and repel each other. The interaction is mediated by gauge bosons, otherwise known as field particles. Now, we know there is a huge difference between the mass of the gauge bosons for the weak interaction. These are in the 80 to 90 GeV range, versus the gauge particles for the electromagnetic interaction, which is photon, and for the gravitational force, which is graviton. Both photons and gravitons are massless. Okay, this is weird. How do you explain the huge difference between their masses? And it turns out there is a theoretical way of doing that is by means of what's called Higgs field. The Higgs field. The Higgs field has, this theory can explain the huge discrepancy in the masses, but how do you observe the Higgs field? It turns out there is what's called an elementary excitation, something supposedly observable. It's called a Higgs boson. So if you can find a Higgs boson, by the way, it hasn't been observed yet. If you can find a Higgs boson, then it means the Higgs field does exist, so you can explain a lot of these things, such as the huge mass of the field particles for the weak interaction. It turns out a Higgs boson is elusive because it's got a huge rest mass of 107 GeV or up. This is the lower limit. Okay, the Higgs boson is so important in our understanding of elementary particles that in popular culture it is often referred to as the God particle, even though to a serious particle physicist, this is probably not a good term to use because the Higgs particle doesn't explain everything. Okay, it does give us a lot, but it doesn't explain everything. So we shouldn't quite call it the God particle, but it's extremely important, and we're still looking for it. And hopefully, with the Large Hadron Collider LHC in construction and operation, we hopefully, will find it pretty soon. All the stuff I've been talking about in this chapter, the interaction scheme and quarks forming hadrons and leptons being truly fundamental particles participating in they do not participate in strong interaction, that sort of thing. All this knowledge is part of what's called the Standard Model. The Standard Model. The Standard Model combines our understanding of the electroweak interaction and our understanding of the strong interaction. And here is a flow diagram of the scheme of the Standard Model. You have mass, matter, and energy. They can exert force, and these are the particles or constituents which participate in these interactions. We have quarks and leptons. These are the particles, okay? And there's 6 quarks and 6 leptons. And quarks can exert strong interaction on each other by exchanging gluons. Photons are the mediating particle for electromagnetic interaction, so electromagnetic force. Leptons, such as electrons, or even quarks. Quarks are charged as well. So quarks and leptons can exchange photons to interact electromagnetically. And the weak force is facilitated by W and Z bosons. So they are the signature of leptons only. All right. So leptons can interact through electromagnetic, weak, or gravitational force. Quarks, that's for strong interactions only. They can exchange gluons. They can, exchange photons because they also, electromagnetic interaction. And then they also participate in gravitational interaction. Everything participates in gravitational interaction as long as you have mass. Now you see there's a dashed line here because in 1979, a Nobel Prize was awarded to 3 physicists for their work on unifying the electromagnetic and weak interaction. It turns out at high enough energy, these 2 forms of interactions really manifest into one. They're actually the same thing. But at lower energy, they look very different. This guy is extremely massive. These are extremely massive. The photons are massless. Again, if we find the Higgs boson, we can understand why there is a break of symmetry between electromagnetic and weak interaction. This theory is called electroweak theory. So in principle, the electromagnetic force and the weak force really belong to the same general theory. It's called electroweak theory. We have then united these two forces. How do you put the strong force under the same umbrella? That is a different thing. If we can do that, we put the strong force, weak force, electric force all under the same umbrella. That is called GUT, the grand unified theory. With strong force also under the same general description with the weak force and electromagnetic force. We're still working on that. Okay, scientists are still working on GUT, the gut. But what about the gravitational force? You know, Einstein studied the gravitational force extensively. In fact, his general theory of relativity is the theory of gravity. So Einstein spent decades after his discovery of general theory of relativity. He spent decades trying to unite the gravitational interaction with these other forces, and despite his ingenuity, he did not succeed. He did not succeed. But he did inspire generations of physicists after him to do the same thing, and that is they try to write down a theory that would encompass all these interactions in the universe to form what's called TOE. What is TOE? Theory of everything, okay? Theory of everything, because this single theory would explain all these interactions. That's all there is in the world, in the universe. So that would be the true ultimate theory for everything in the natural world, in this entire universe. We're still working on that. Now let's examine the issue of particle reactions. You put particles together, what happens, if anything, and unstable particle can decay into other particles and so on and so forth. These are called particle reactions and decays. In order to see whether a certain reaction takes place or not, we need to observe what's called conservation laws. We have the conservations of energy, moment, and angular moment, and those things we already know. And of course, conservation of charge, all these we already know. It turns out that in order to explain why certain reactions take place and certain reactions cannot take place, we must add new laws, new conservation laws. And what's the idea behind these new quantum numbers, like the baryon number, lepton number, even there's something called strangeness, and of course there's topness, bottomness, and so on. What's the idea behind all these new quantum numbers? Well, there are actually two things. First of all, these quantum numbers give added dimension to the quantum state of this particle. Okay, it turns out this particle is not only described by its mass, by its charge, electrical charge, it's also described by its baryon number or lepton number or strangeness and so on. These are just added quantum numbers which are necessary to complete the description of this particle. Without these quantum numbers, you cannot know fully the state of this particle. That's one thing. Another thing is that it turns out that in certain reactions, some of these numbers are conserved, not all of them, depending on what kind of reaction it is. They're conserved. And that is important because that tells us, okay, this reaction can take place, that reaction cannot take place, and so on. It's very important to us. So we have to go beyond the basic three conservation laws plus the conservation charge. We have to go beyond that. For example, strangeness. This quantum number, strangeness, is forced upon us. It was forced upon us. In the 1950s, people discovered a whole bunch of baryons. The kaon, this is the lambda particle, this is the sigma particle. These are all massive particles, and they decay into other smaller, lighter particles. Okay, and here is an example. A pi meson plus an electron can produce a kaon and a lambda particle. This process has been observed. It does proceed. However, this does not happen. Okay, in other words, if the lambda particle you replace with a neutron, it turns out this has never been observed. And you know, there is nothing wrong with this reaction if you look at all the existing or known conservation laws. Conservation of energy, conservation of momentum, angular momentum, charge, and so on. Nothing is violated. So what's stopping it from happening? There must be something else. Okay, and it turns out, according to today's quark model of these particles, it turns out these guys, the kaons and lambda particle and sigma particle, these particles are different from all other hadrons in the sense that they are partially made of a quark called the S quark, the strange quark. The S quark has a new quantum number, it's called strangeness, and the strangeness must be conserved for all strong interactions. This guy is assigned a strangeness number of positive 1, this guy negative 1, so it's 0, add them together. This is not a strange particle, this is not a strange particle, because they don't have any what's called strangeness, and therefore you have S equal to 0 and S equal to 0, that works. This doesn't work because you have 0 strangeness, and here is a strangeness of positive 1, and the neutron is not a strange particle, so you go from S equal to 0 to S equal to 1. That is forbidden for strong interaction. Delta has to be 0 for strong interaction. However, for weak interaction, delta S does not have to be 0. It doesn't have to be conserved. Now, therefore, a kaon can decay into a pair of pions. Okay, you have S equal to 0, S equal to 1 going to S equal to 0. Strangeness is not conserved, but that is a weak interaction. How do we know that? Because the decay does not happen very quickly. It happens in about 1/10 billionth of a second. That sounds like very fast, but it's nothing compared with the characteristic time scale for the decay to proceed if it's a strong interaction, which will take place in 10 to the negative 23 seconds. Okay, 10 to the negative 23 seconds. This time scale is actually the signature of a weak interaction, which takes considerably longer. So now let's do something fun. We know all the conservation laws, and the question is, can we apply these conservation laws to predict whether certain things can proceed and certain things cannot proceed? And so I have written down a few interactions, mostly from the textbook, and we can use the conservation laws that we're familiar with to see whether any of these can proceed or not, and if not, what's stopping them from proceeding. The first one certainly can proceed because we have written this down many times. This is a famous reaction for the decay of neutrons in free space. Neutron become a proton plus electron plus a anti-electron neutrino. Let's see here. We have to observe all these quantities, okay? E and P. First of all, energy momentum. Let me say something here about conservation of energy and conservation of momentum. You don't have to worry about conservation of energy unless there is only one particle on the left side. Okay? If there are more than one particle like this in this case, even if the final particle is far more massive, in theory this can still proceed, because what if I can give these particles a lot of initial kinetic energy, right? They collide with each other at high speeds. So that's typically what happens in particle accelerators. You have lighter particles colliding at extremely high energy. They can produce very massive particles as a result. So unless there is only one particle to begin with, then if that's the case here, the final particles cannot have rest mass greater than that one, because I can use the reference frame in which this guy is at rest. So in that reference frame, there is no kinetic energy. Okay, so you cannot possibly produce something heavier than yourself. So conservation of energy only is relevant when there is only one particle to begin with. What about the conservation momentum? The conservation momentum is only relevant if the final state has only one particle. Like in this case, a pair of electron-positron producing only a single gamma-ray photon. This does not work. Okay? This does not work. Why? Because, again, like I said before, you can have a rest frame, you can have a center of mass frame for these two particles with zero momentum, but afterwards, you don't have a zero momentum anymore. So that's a problem. Now, if the final product is not a photon, which is unique because it always travels the speed of light. If it's something else, then it's possible as long as the initial momentum adds up to 0. So those are the things you have to consider. Okay, but only if the final particle there is only one, then you have to consider whether momentum conservation is being violated. Now, look at the third one. Is there something wrong with this at all? Proton, antiproton. So that produces a total charge of 0. The final product, total charge of 0. So don't worry about energy momentum, okay, because the two particles here, two particles there. Charge conservation is also true. What about conservation of baryon numbers? Conservation of baryon numbers. Okay, here is positive 1, this antiparticle negative 1, so it's 0. And these are not baryons, so baryon number is also conserved. Okay, strangeness, don't worry, these are not strange particles at all. Only kaons, lambda particles, and sigma particles. So that's not a worry. What about lepton numbers? Those are not leptons, so lepton number is 0. Those guys, okay, now be very careful here. The original muon was discovered to be a negative muon. That's historical. so we call this, because it first discovered, we say L equals positive 1. So mu positive is assigned to be negative 1. That's just a convention. Okay. The original electron was discovered to be a negative particle, so we give it L equals to positive 1, and therefore positron has no choice but to be negative 1 because of the antiparticle. Okay, now, so this has a lepton number of negative 1. This has a lepton number of positive 1, right? Look at this. So it appears the lepton number is also conserved. It's also conserved. So we have 0 to 0. It looks like this thing can proceed. But guess what? It cannot. Okay? So what is wrong? Well, it's something that I didn't tell you, so it's not your fault. And that is when it comes to lepton numbers, there are 3 different types of lepton numbers. The 3 distinct type of leptons, electrons, muons, and tauons, you cannot exchange them. This is L mu. This is LE. You cannot substitute an LE for L mu. They do not mix. Okay? So therefore, this process cannot take place because you have a negative 1 unit of lepton, of a muon lepton number, and you have a positive 1 number for electron lepton number. They do not cancel each other out. They have to be separately conserved. L mu, LE, and L tau. So that doesn't work. Okay, so that doesn't work. What about the next one? Gamma plus P equals N plus pi naught. Well, this one is obvious. There is no conservation of charge here. This guy is charge neutral, positive 1, 0, and 0. So that doesn't work. Okay, here is an electron neutrino plus P. It gives you N plus E, so conservation of charge. That's valid. Let's worry about, there's no strangeness. There's baryon number is also true. There's 1 baryon, 1 baryon. Okay, no problem. But let's look at conservation of lepton numbers. Let's be very careful about that. Nu E, okay? Nu E, what is the lepton number for nu E? Okay, now in this, you see this here? This is the electron with a lepton number, electron lepton number of positive 1. This is negative 1. Okay, that's what we call it anti-electron neutrino. The electron neutrino has a lepton number of positive 1. So here is positive 1 here. And what about this guy? What about this guy? This guy has a electron lepton number of negative 1. You see that? Okay, so I have a positive 1 here and a negative 1 here. Does this work? No, it doesn't. It works if you put a nu E bar here, because a nu E bar is an anti-electron neutrino with a lepton number of negative 1, which matches the lepton number of this guy, also negative 1. Both are electron lepton numbers, so they conserve. They would conserve. You put a bar here. Otherwise, it does not work. Okay, what about a proton decay into a positive and 0? We know conservation of charge is valid. Okay. Is there something that's not valid? Well, baryon numbers. Positive 1 here, 0, 0. So it doesn't work. Okay. This one, what do you think? Positive to positive and 0, so conservation of charge is valid. Okay. What about conservation of lepton numbers? Okay, we have to be very careful about this. This guy has a muon lepton number of negative 1. This guy, what about that? Well, the original muon is associated with a anti-muon neutrino, just like original electron is associated with an anti-electron neutrino. So anti-electron neutrino has a lepton number of negative 1, just like anti-electron muon, anti-muon neutrino, anti-muon neutrino, nu mu bar has an L mu of negative 1. Okay, so this this neutrino, nu mu neutrino, not the anti one, should have positive 1. That's, because they're antiparticles with each other. So this is positive 1, and this is negative 1, right? Negative 1, because you see here negative 1. So this works. Okay, this actually works, believe it or not. Okay, now here, this one is strange because you have an actual particle on this side. This particle is charge neutral, so there is no problem with Q. There's no problem with baryon number because 1, 1, 1, 1, and this is 0, so don't worry about it. These are no strange particles. What about lepton numbers? None of these are leptons. So guess what? This creation, at least in theory, is possible. This new particle, if you have enough energy to begin with, one going this way, one going that way, they collide at high speed, you can produce this. Okay, there is nothing wrong when it turns, you examine all these conservation laws. So that's fun, isn't it? All right, now next, let's take a look at what's missing in these reactions. Can you figure out what to put in these reactions? Okay, the first one, you have a pi meson decaying to a neutral pi meson plus a positron, so no charge is already conserved. So what's left is a charged neutral particle. Why do we even need this particle? Because you have a lepton here, okay, which is the electron, with a lepton number of -1. You have to balance by an electron with a particle with electron lepton number of +1. What's that? What's that? Well, for this guy we have -1, so it must be nu e. Okay, nu e. So that's the electron neutrino, not the anti-electron neutrino, because of the balance the electron lepton number. Here you have something plus p equals mu bar, and mu negative plus p plus pi bar. Okay, so positive and negative cancel out. You don't have to have any charge here. This guy is also charge neutral. In fact, all these are neutrinos, it turns out. This is a neutrino. What kind of neutrino does it have to be? Well, on this side, you have a muon with a muon neutrino number of +1. Okay, you know, the antiparticle is -1. This is +1 here. So you need a muon neutrino number +1. What is that? Well, the original muon is associated, is negative associated with this guy, with -1. So this one is the one with +1. So therefore, you have to, so you have a negative, you have a +1 here. You have to add a +1 there. That's nu mu. Okay, that's what it is. It's the muon neutrino, not the anti-muon neutrino you have to put in. It's just a matter of satisfying the conservation laws. And this is a strange particle. It decays into, but it's a strange particle. We don't have to worry about this though, because it's a weak interaction. Strangeness is not conserved. P plus mu bar. This is positive, this is negative, so that, you know, charge is also conserved. This is a charge neutral guy. What do we need that for? To balance the muon neutrino number. Okay, this guy has a muon neutrino number of +1. You see here. How do we balance it? You choose -1. So it's nu mu bar. So it's got a negative muon neutrino number. Lastly, you have a tauon decaying into a muon plus plus two other particles. Why do we need two other particles? Because the tauon and muon are both leptons, but they belong to different categories. This is a tau, this is a mu, so they have L mu and L tau, both have to be separately conserved. Okay, the tauon, original tauon, was discovered to be as a negative particle with sign lepton number to be +1. Here you have a positive tauon, which is the antiparticle of the first discovered one, so its L tau should be what? Should be -1, right? So you choose something with L tau -1 to balance that, and that is the tauon. This is the anti-tauon neutrino, nu tau bar. Next, there is mu positive with a muon neutrino number as -1. You have to balance it with +1 here, +1 here, nu mu. See, that is how we play this game. It's a matter of satisfying all the conservation laws. So, we had a lot of fun studying particle physics, but what about the other side of the story, the realm of the ultra-large, the universe, the galaxies, the stars and galaxies, and the universe itself? In other words, we're going to take a brief tour of astrophysics and its association with the world of very small, with particles. We do that as our last lecture of 1D coming up.